Hello and welcome back. Today we are going to talk about robotic palletizing. As you can see in this video, this robot is palletizing cases of product. I'm not quite sure what they are, but it is placing them in varying orders depending on what layer and what position within the layer the robot is working on. You will notice the grippers are designed to actually pick up both of the cases simultaneously, so two at a time. However, you'll notice that it actually is treating them as two separate things. It's not picking up both cases simultaneously in the sense that it is a single action. And you can see here that it is actually placing them separately, which is what I was getting at. And part of what is happening is that it is making a decision on which way to process the pair of cases based on the layer count and the position within the layer. The paths to and from each placement location should also be paid attention to because, as you can imagine with this, if you don't approach and retract from each pair of cases, you run the risk of having the robot hit the preceding cases or, even worse, cases on the next layer down. This next video is picking up long, thin filters of some sort, and you'll notice that it is only putting them in a single set of rows or columns, depending on your point of view, but it's not multiples like it was in the preceding video. It is smart enough to pause when the box is full and is able to then cleanly translate to the next box based on the inputs and outputs in the robot cell. So this video has been included because of the unusual gripper. You'll notice it is holding an empty bag. It just grabbed the full bag, is now placing the empty bag on the machine for filling, rotates the full bag, and then figures out where to place it. Even if the bags were fairly light, and I don't believe they are, the size of that gripper in a lot of ways will dictate the minimum required capacity for the robot arm because of the large size of the gripper and what is probably a significant amount of weight in that gripper. So this is fairly common to see companies do a simulation of their solution before committing to it. A lot of that is part of the process for bidding and winning the project contract. And so you see two fairly large robots here, feeder systems for the pallets. And so the company who created this is going to have to understand more than just the robots themselves. In this case, we are seeing the robot being fed from both sides, and part of the reason behind this is utilization and ensuring that the robots are ensuring that the robot's usage is being optimized, and instead of worrying about increasing the speed of the production line, they're able to have a single robot process two different production lines. From the point of view of designing the gripper, bags such as these that are extremely pliable and very easily change shape are much more of a challenge than rigid boxes or even bags that are stiff. And so as you can see here, the gripper is designed with number of fingers that reach under and grab the bags. And the way this is palletizing has been set up so that it's almost dropping the bags onto the pallet where they belong. And so instead of worrying about approaching the pallet very, very carefully like we saw in the first video, this application allows for a lot more forgiveness in the robot path. Speaking of grippers, there are a number of things that have to be considered as you design the gripper, as you select a gripper for usage. Things like the product weight. Is the gripper strong enough to grab the product? Think about the last video we just watched with the bags of salt. Those are probably 40 or 50 pound bags of salt. And so those fingers need to be sufficiently rigid and strong to lift up those bags, but you also need enough of those fingers to ensure that you don't tear the bag, puncture the bag with the fingers, things like that. You need to be aware of what the surface texture of the products you are picking up is. And something as simple as cardboard really isn't even that simple, because some types of cardboard are more porous than others. And if you are using a vacuum to pick up the cardboard, you have to be aware of how much vacuum needs to be generated to ensure that you are able to actually pick it up and that you are generating enough suction to overcome any porosity in the material. You have to pay attention to how rigid the product is. And then you have to pay attention to the spacing. And so that first video where they were loading the pairs of cases of product, the spacing was a big deal because you couldn't come in from both sides. They worked out a solution where you could come in from one side, and that seemed to have worked really well. In the last video with the bags of salt, they were not as worried about the spacing. They were not as worried about ensuring that the bags were tight up against each other necessarily. A properly configured pallet has a couple of key features. The first feature is that there is no overhanging components. The first is that product does not overhang the edges of the pallet. The reason you don't want this is that it puts stress on the product. It also is a point for snagging when you're moving the pallets around, and can very quickly result in the items on the pallet being knocked off, pushed off, forced off, or just plain falling off. A lot of the time, the products on pallets are what is referred to as interlocked, and you can see that on the screen here on the lower right. And this is where the products lend additional rigidity and support to each other by virtue of not having all of the seams line up as you move up the layers in the pallet. The design of the palletization of products onto a pallet is really outside the scope of this class, and so I'm not going to say anything else about it at this point. However, be aware that it is important, and generally you are going to be told here's what the pallet needs to look like. At that point, you have three choices. You can manually program every single point on the pallet. You can do what's called a calculated routine, or you could do what's referred to as a canned routine. And so if you're doing your own calculated routine, there is an assumption that you are trying to be efficient with your code and that you are calling the same segment of code multiple times with some sort of an offset or a indicator to inform the robot of where exactly it needs to go for the next bit of movement. So what you see on my screen here now is the logic for trying to do a calculated palletization routine of a single layer. As you can see, you would set X and Y to 0. They are the current count. You go get the part. You move to some sort of base position, some known location where all calculated activities are being based off of. You check to see if your current count is equal to your target count. If it is not, then we're going to go down and calculate the offset for the X, and then we're going to increment that X and move to the offset position. Repeat the process, go get a part, move to the base position, check to see if we're at our current target count. If we're not, calculate the offset, increment X, move to the offset position, and repeat the process over and over. When your current count does equal your target count on X, which we're going to call our row for now, we then need to increment to our next row, Y being columns, and then we calculate our offset, increment Y. We're going to set X back to 0, recalculate that X offset. And so, for example, we've gone through positions 1, 2, 3, and 4, as you can see on the screen. The incrementing of the Y offset moves us from that first row to the second row at number 5, and then setting X to 0 and recalculating the offset moves us from our position at 4 back to the equivalent of position 1, but in the second row, which gives us position 5. Repeat until you are done with your pallet. So our final option is a canned routine. And this is a scenario where you feed some basic information to the robot controller, and it will take that information and be able to process it in a way that will allow it to extrapolate out a significantly larger amount of information and also automate the calculations of the previous discussion. So the images here are from the FANUC robot manual, and they show us some of the terms that you may see used when talking about palletization. In the middle section here, what we're looking at is this path pattern, and you'll hear people talk about the approach points. And so this is approach point 2, this is approach point 1, this is my stack point, my retraction point 1, my retraction point 2. And the reason you want this is you don't want to come in through, if I were to come in from over down here, I might hit the existing product. If I come straight down, I'm fine, but that is not always the fastest and most efficient path for the robot. You can have 1 approach points, 5 approach points. It's really solution dependent. In the example here, we have a row going this way, columns are going this way, and then we have layers. Layers are the Z for our example here. When you're doing a canned routine, depending on the system, you may have something like this, where this is basically a wizard to walk you through how to do the palletization, how to configure it, how to define it. It will ask for things like a pallet register or some sort of identifier so that you know which pallet you're talking about, because probably the system is able to support multiple pallets simultaneously. It will need to know things like the order in which the pallet is being processed, and do I do it in terms of row, column, then layer, or do I do column, then row, then layer? And it really depends. Am I going across and then up, or do I go up and then across? Auxiliary positions get to the idea of pallets where I have odd shapes or odd patterns in them. And then when I go to teach the pallet to the robot, generally what I need to teach are some variation of these 4 points. And what I'm teaching is here, the 111 lower left, the 411 is lower right. In this case, the 131 is the back left, and then the 115 is the top left. Now this assumes that all of the products in your pattern are the same size, and that the positions that they're being placed are evenly spaced. If either of these assumptions are incorrect, you cannot use this type of canned routine. That's not to say there aren't canned routines that support that, but more common routines you're going to find on every single reasonable robot controller aren't necessarily going to support unusual pattern shapes, odd spacing, things like that. For the Mitsubishi robot controller, there is an instruction to define the pallet. And so you see here on the screen some screen captures from the user manual, and it looks like a lot of information, but it's not too bad. We start with the define, and then we say what pallet number are we defining. In this case, we're going to define pallet 1. What are the points, those corners, that I need to define so that the controller is able to calculate where everything belongs? They are points 1, 2, 3, and 4. As you look down here, we have a start point, an end point B, and then the diagonal point. And if you teach those in a square pattern or a rectangular pattern like you see here, you will get a nice square, even palletization routine. If I move the diagonal over to here, leaving everything else where it is, as I move up the column on each row, my spacing will end up being at an angle, because it's going to teach 3 points here, but if the spacing, instead of being equal, goes from here to here, that middle point would be here, and so it would go 1, 2, 3. Hopefully that makes sense. I then need to tell it how many positions are included in my pallet, and so 4 and 3, quantity 4, quantity 3 for A and B. And so I'm saying I've got 4 in this direction, 3 in that direction. And then finally, what sort of pattern do I want to go? This goes back to that row column layer or column row layer in the FANUC manual. One of the limitations of the Mitsubishi controllers is that they only define a pallet for a single layer. And so I have the option of either going 1, 2, 3, up 4, 5, 6 in a zigzag pattern, or I can do 1, 2, 3, return back to the left, go up 1, go across, return back to the left, go up 1, go across, and that's what they mean by same direction. And then I also have the option of doing an arced pallet. And so this is what a palletized routine would look like in code. I've got my counter on line 10. I define the pallet in line 20. I specifically have left out a lot of the intermediate steps in this program. So I say move to point 1 to get the part. If you'll notice here, I've not picked the part up. I've not waited for the part. I've not included approach points. I've not included retraction points. This is meant just to give you the bare bones idea of what your program skeleton would look like. So in line 40, I set point 10 to equal the information from pallet 1, position 1. Pallet 1, position 1. Move to P10, increment my counter, go to 30, get the next part. Now I'm setting P10 to equal pallet 1, position 2, because I've incremented my M1 variable, and so now I'm going to position 2. Continue through until it's done. You'll notice I don't have logic to say stop when I've hit the max size of my pallet. You will need to add that type of logic into your program as well. So here is a fairly simple palletized routine. I have, as you can see, created a gripper. I created a part that's going to be moved off of this conveyor into this holder area. I've got my counter that we talked about. I've got my pallet definition, my loop. I'm moving to my clear points and my approach points. I've got the delay for the hand in there. I've got the logic to place the palletized data into my variable where I'm going to be placing the part. I'm using the offset on the place, incrementing, looping, and then halting. And so I brought up the program monitor so we can watch the program and specifically watch the position information down here. The first two values, the X and the Y, you'll see those change as line 130 is executed. You will notice that we are doing a Palletize routine 1, which is Zigzag. We went there, we're going to go here, 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 then there. And our program is finished. Now, if I change the Palletize type to 2 for same direction, when I run this, you'll see after it goes here, it jumps back up to there and then continues in the same direction. And so that's a Palletize routine. I know this has been a long one, but that's it for now. Thanks.